Good morning, Michael.
Good morning, Matt.
I think we're doing applications again.
We are. I was thinking we could do something about least squares. And you know a bit about least squares because of your machine learning. You want to say something about that?
Yeah, in machine learning, we actually are trying to fit data to a model. And what we're going to look at is the simplest model. But if you look at it carefully, it's one of the basic underpinnings of what we call neural nets, which are application over application of this idea, but in multiple dimensions. So let's start with the simple case where we just have one unknown that we're trying to find.
Okay. I was thinking of maybe a physical experiment because that's sometimes easier to explain. So I was thinking of a weight on a spring. If you attach a weight to a spring, the spring extends. And if you put more weight, the spring extends even more.
Yeah, Hooke's law, right?
Hooke's law, exactly. So we have a spring, and we can attach a weight to it, and it'll extend a certain amount depending on how much weight I put there. If I call this X for the weight and Y for how far it extends, I can make a little chart. So here's X and here's Y. Maybe X is measured in grams or something like that, and Y is measured in, centimeters. So maybe if I put 1 gram, this stretches 3.1 centimeters. And then if I put 2 grams, maybe this is 6.5. And then maybe I'll put 4 in, and it comes out to, 13.7 or something like that. And I can do a bunch of measurements, right?
Yep.
If I do a little chart, I'll get a little, so here's 1, 2.
You're going to take each measurement and put a dot there, right?
Yeah, so I'll get, okay, maybe my dots are a little bit higher. But I'll get some collection of dots, and maybe I'll do all sorts of weights.
But now when there's no weight, Y is 0.
0, so it
So
probably
that
looks like it
put-
goes through here,
It
right?
goes through the origin.
Yeah.
Now that sort of looks like, if we want to say, what's the best way to describe this scatter plot, as it's called, because the points are scattered. Well, it's not going to be some complicated thing like a sine function. I guess the simplest function we know, in this case, going through the origin, is Y is equal to proportional to X.
So maybe Y is K times X.
And we want to find K.
Right, and so you want to pick the best line. This is kind of a bad line. This is a bad line. Somewhere in between is a good line. Okay?
So actually, when we try to do this, like if we were carpenters and doing this kind of thing, trying to find a line through a bunch of nail holes or something, we would try to move this whole line around, so we would move this. So this is our model, and we can actually try to find it from the data.
So that's right. So this is the guy we want to find. So we want to find, it's like finding Nemo. We're finding K.
Or a lion.
Or a lion. So we've got some data, we've got a model, now we want to fit the model to the data. Now one standard way to do this is you take a measure of how good the model is at predicting the Y value. So if I put in one of my X measurements here, I get an estimate for Y. And the difference between the measured Y and the estimated Y tells me how good the problem is. So if I take some sort of X, let's say x1, and I multiply it by k, and I subtract the measured y and square it. This gives me an estimate of how good or how bad k was in estimating this. Now, of course, I can make this 0 for one measurement by taking the right k.
But then it won't fit all the others.
It won't fit all the others. So why don't I add up all of these guys? I'll call this yi, xi. I go through the whole list from 1 to n. N might be a 10, it might be 100. In a neural net, it might be 1,000,000.
So I understand why you want to square this, because you don't care if the error is positive or negative. You want to just get the error, so you have to square it. But you could have changed this number. You could have put 4 or something even so that negatives don't come in. How do you pick that? Like, where does that come from?
So this comes from some deep statistical ideas about you've heard of the normal distribution. Typically, when you have errors in a physical measurement, they are distributed normally. This turns out to give you sort of the highest probability estimate. Some deep statistics there. What I like about it is when you write it down this way, it's easy to compute the derivative.
Yeah.
Yay.
Yeah, okay, especially we only have one unknown. So this is a function now of k.
So let's call this is my error function. And you're right, the data is already given, so this only depends on k. And that's the thing we're trying to minimize. We want to minimize the error.
And in neural nets, we have exactly this. The output of our net from a gold standard reference gives an error, and we try to figure out the best way to represent and minimize that error so we're good at predicting things.
Exactly.
Just like here, once you have the k, you can predict a point that you didn't actually measure.
Right. So let's see if we can get a formula then for where we minimize the errors. Now this is a continuous function. Everything's nice and polynomial, looks very pretty. We only care about k values that probably run from something like 0 to maybe 10 or 100. So that will be a closed interval. We know that continuous functions always have a maximum and a minimum on a closed interval.
So we want to minimize e
They minimize e. Where does the minimum happen?
when the derivative is 0.
So let's compute the derivative.
And we're going to use the chain rule.
That's right. So we're going to have a sum. So let's put the sum here. Here's something raised to the 2 power. So if it was like x squared, what would be the
It would
derivative?
be 2x.
So it would be 2, we're using the chain rule, 2 of whatever was inside the thing.
And now we differentiate what's inside.
And we differentiate with respect to k.
Well, that's xi.
So we get it multiplied by xi.
Is there a minus sign?
Ah, yeah, let's put the minus sign up here.
That comes from the derivative of this yi minus kxi, that linear function with respect to k is minus xi, right? So-
That's right.
Okay.
Now, the minimum happens when the derivative is 0. So I get this formula. Actually, why don't I? Oh no, I'll just copy it down line for line. For this to be equal to 0, okay, the minus sign doesn't matter. Plus or minus 0 doesn't
Yeah.
matter. The 2 doesn't matter, so
Yeah.
we can get rid of the 2. So now I'm left with the sum. I've got an xi times a yi. So this is a sum, yi times xi. And I'll put the sum over here. K is a constant, so I can bring it outside the sum. Then I have an xi times an xi, so that's xi squared. That's equal to 0. Now, Matt, can you solve for k?
Well, we take this to the other side, get rid of the minus sign. This is some number, so it's this number divided by that number.
Very good. So k is equal to this number, yi xi, divided by the sum of the xi squared. And that's our formula for the best slope to this line to fit our data.
Wow. Is there any statistical thing, like this is like the sums of the squares of the independent variable, and this is like a dot product of two vectors?
This is like a dot product, so it's the correlation between these two vectors. And this is a normalization factor that sort of averages out the values of the squares.
So when you say correlation, we know it's a dot product that's projecting one vector onto another. So it's the projection of the independent variable, the xi's, and the dependent variable, the yi's.
That's right. And there we have it. How do you fit a straight line to data? You use this formula.
Fantastic. What a great explanation and what a great example, because in higher dimensions with a little more math, this is what we do with neural nets.
Thanks, Matt.
Good to see you, and next time.